Hello, my name is Andrew Miller, and this is estimating heat transfer coefficients and thermal resistances in a cooling cylinder. The objective of this experiment is to estimate the heat transfer coefficient, H, from a cooling behavior from a hot cylinder. The second objective is to then calculate the equivalent thermal resistance. I will then visualize the temperature distribution and the final thermal state of the cylinder. The overall experiment is to take 2 liters of warm water and put it in a plastic water bottle. I will then place that bottle in the freezer for 1 hour and determine the H and R of the container. This will then be used as a control, and afterwards, 3 jackets of different materials will be used to test for their insulation values. All experiments will have 3 trials so that their values can be averaged. This is some images of what my experiment will look like. You can see on the right that this is being able to heat up the water using a temperature probe. I make sure to mix the water to get the cup mixing average temperature, and then I place it within a water bottle for my first set of trials to find the thermal resistance of my plastic water bottle. These are the 3 different jackets I will use. The one on the left is designated as RA jacket and is a US thinner jacket. The one in the middle is designated Columbia OmniHeat 2. And the one on the right is designated as thick jacket because it is very thick. And for each of these, I will have to modify the radius of my cylinder to match the jacket's size. The physical setup of this model is that I will model this as a cylinder with stacks of 2-dimensional disks with the radius of 0.0625 of the water bottle. This radius will then be increased based on which jacket I'm using. The initial and final temperatures are recorded, with the initial temperature being at 0 minutes and the final temperature being at 60 minutes. It will be exposed to a constant ambient temperature of negative 19 degrees Celsius in the freezer, and the cooling will be done by convection, assuming that there will be no internal heat generation from water. The mathematical model was something that we have all experienced in Transport Phenomena 1. This is a transient heat conduction solved in 2 dimensions, where we are using Fick's law, del T, del time, equals alpha, which is the heat transfer overall coefficient, times del squared temperature. And we can see here that this model, because we are using cylindrical coordinates taken from the Transport Phenomena 1 textbook, is quite complicated and is actually, for this situation, not able to be solved by hand without making heavy assumptions. Because of this, we will be making heavy use of a mathematical model used in MATLAB. So, we will be using the boundary condition that at outside of the water bottle or the jacket that it is a constant negative 19 degrees Celsius, so that we can set up the negative K del T is H, the constant we're solving for, T minus temperature ambient, which is that negative 19C. We will be using the known constants for water, assuming that the thermal conductivity of water is 0.6 watts per meters Kelvin, the density of water is 997 kilograms per meters cubed, and the specific heat is 4,186 joules per kilograms Kelvin. The assumptions that this project is making is that the water bottle and jacket are a perfect cylinder, which is not exactly true, but it is close enough for the sake of modeling, that no air is trapped between the bottle and clothing, the freezer maintains a constant ambient temperature of negative 19 degrees C, that the material properties of water are constant and are not a function of temperature, and that only convection is modeled. The simulation method, because this cannot be solved by hand, is the MATLAB partial differential equation toolbox. Now, the model is created using the equation create PDE with thermal and transient, and the citation below is links to the MATLAB documentation for create PDE. The circular geometry is defined with descript G, where we set up a convection boundary condition that's applied to all the edges of this circular geometry. Then we set up optimization with fmin search to find the best heat transfer coefficient that yields our target temperature based on our boundary condition set up in the previous slide. The point of this experiment is to compare our results of H and R with the percentage of material. Our RA jacket is 50% cotton and 50% polyester with no special coating. The thick jacket is 100% polyester with a PVC coating, and the OmniHeat jacket is 100% polyester but with a metal coating, either gold or silver. and this can be seen within Columbia's website for OmniHeat. The temperature field of all of our models looks similar below, where essentially the highest temperature is at the center of the water, and then it decreases in temperature getting towards the boundary condition. Is in these bar graphs below, that the H average of the bottle, of course, is higher because there's no insulation, with the resistance being lower, and the RA jacket being the lowest, the thick jacket being the second highest, and the OmniHeat jacket actually having the highest thermal resistance. Now, the reason that this is interesting is because the jacket on the right-hand side, this brown in the bar graph, is actually a lot thicker than the OmniHeat jacket. While in terms of convection, this may not make a lot of sense, considering that the thicker piece of insulation has a lower thermal resistance. However, this neglects radiative heating, which is found in the Omni jacket due to the metal lining on the interior. So in conclusion, there are multiple modes of heat transfer that we deal with daily, and while most people think that a thicker jacket means a warmer jacket, thermal radiation on the interior of the material plays a bigger role than we think, so that when companies are designing a jacket, you should look at not only the conductive heat transfer, but radiative heat effects too. So, our results. If I were to do this experiment again, I would also model radiative heat effects. However, it is difficult to model these within MATLAB, as the Create PDE toolbox only models convective heat transfer. These are my citations used for this experiment. The appendix of my MATLAB code used to model. You can see here that the only difference between HR bottle and HR jacket are the initial and final temperatures. Everything else is the same. Thank you and have a great day.